Now, let's say, for example, if you have more than one substituent on the benzene. Let's say if you have two substituents on the benzene and you want to introduce a third substituent on the benzene. Then in this case, these are the rules that you need to follow. First, we're going to check each group, what position it directs. If they direct the same position, then the groups will reinforce each other. Let's have an example over here. So we are forming from this reaction a Br positive charge, and this is what we are going to add. This is going to be our electrophile. So the first thing that we do is we look at the substituents on the benzene and see what positions they direct. So the OCH3 is a strong activating group. So this is an electron donating group. It is a strong electron donating group. And that strong electron donating group, it directs two positions. It directs the ortho position. We do have two ortho positions in this case. And the ortho position, if I start numbering from the substituent, is going to be on the second carbon. Okay. And it also directs the para position. And the para position is on carbon number 4 from that substituent. So you have 3 and you have 4 in there. So we have two ortho positions and we have a para position. Normally, we want to avoid static hindrance. So if this bromine adds to this carbon, we're going to have an accumulation of 3 groups on the same side. We want to avoid that. So to avoid this, we are going to cancel this product out. This product does not form because of static hindrance. So we're going to take that option out. And this makes now two options over here where the Br positive can add either on this carbon or it can add on this carbon for this strong electron donating group. Now for this bromine over here, let's go ahead and check. This is a weak deactivating group. So this one is an electron withdrawing group, but it directs the ortho and the para. So both they direct the ortho and the para position. So for the bromine to direct the ortho and the para position, the ortho position is going to be over here. So the bromine is going to direct again this carbon over here. So these two, the OCH3 and the bromine, they direct the same position. You see that? This is called the group reinforcement in there. Or the bromine can come and direct this position over here, and this is the para to the bromine. So we have, this is 1, 2, this is a 3, and this is 4. So both substituents, they direct the same position. And the Br positive will add either to this carbon or it will add to this carbon over here. So in this case, you will consider all the products, and this is called the group reinforcement, and you will form both products in there. So you have your OCH3, you have your bromine, and I'm just going to write the new bromine that I am introducing in a different color. So the bromine is going to add either here, plus it's going to add, this is going to be the bromine, and the new bromine from the reaction is going to add over here. Always check the products that you are forming if they are different or if they are the same. If they are the same, just cancel the ones that are the same. Do not duplicate. Here, both of those, they are different products, so we're just going to leave them, and both products are going to form. Let's have another example here. From this reaction, I am doing the nitration, so I am nitrating in this case, and I'm forming the nitronium ion. Go ahead and check each group and see what is the position it directs. So the OCH3, this is an electron donating group. It's a strong electron donating group. It directs the ortho and the para position. The aldehyde, this is partial positive. So this is an electron withdrawing group, and it directs the meta position. So we're going to go ahead and do the OCH3 first. It doesn't matter which one you do first. Let's see if they reinforce each other. So the OCH3 is going to direct the ortho position, and you need to know where is the ortho and the para position? You need to know where are the ortho and the para positions relevant to the group. So always make sure that the group that you are adding to is group number 1. And then the ortho is on the 2nd carbon. The para is on the 4th carbon. So the NO2 will add either to this carbon or to this carbon over here. The NO2 for the aldehyde is going to add meta now. So it's going to add over here. So this is going to be 1, 2, and 3. And 3 is the meta position. You can easily see that these two positions, they reinforce each other. So we're going to have a product on this carbon only. And this is going to be our major product. So the nitro group now is going to add in this position. You have the aldehyde and the CH3. Another example, I am forming the sulfonic acid. This is going to be my electrophile. Let's just check those two substituents in there. So the nitro is an electron withdrawing group, and that is a strong electron withdrawing group. It directs the meta position. This one is an electron withdrawing group, and it directs the ortho and the para position. Let's check to see if the groups reinforce each other or not. So the nitro group is going to direct the sulfonate to the meta position. And the bromine is going to direct the sulfonate into the ortho position and the para position. So you can see that I'm reinforcing the product on this carbon, and my product is going to be just one product. You're going to have your NO2, you're going to have your bromine in this case. And you are going to form your sulfonic acid. This is the SO3H on this carbon. You can form the SO3 on this carbon, but see, if you form the SO3 on that carbon, we are going to have all the groups, they are going to be accumulated on one side. So this is going to be the SO3H. So all the groups here, they are going to be accumulated on one side. And if this happens, this is going to be a minor product because of steric hindrance. So it is not favorable to form. This is why the major product is going to be this product only. We normally don't show products that show steric hindrance. So if you are writing a product and you see an accumulation of groups on the same side, just go ahead and ignore that product. Another example over here, we are forming a chlorine electrophile. So you go with each one of these groups. The sulfonic acid, this directs the meta position because it is an electron withdrawing group. The bromine directs the ortho and the para position, and it is an electron withdrawing group as well. So the sulfonate is going to direct the meta position. So the chlorine is going to come meta to the sulfonate. It's on either one of those. Each one of these is going to be the same. Okay, so just go ahead and choose one. And then the bromine is going to direct the ortho position. So you have a group reinforcement in this case. And the para position of the bromine is already occupied, as you can see with the sulfonate. So I'm just going to skip that. So you're going to end up getting just one product in this case. Your product over here is going to be the chlorine on either one of the sides. It doesn't matter because both are going to be the same, and we're going to form the sulfonic acid over here. So here I am adding the Cl positive. Let's check the groups if they reinforce each other. So let's start with the bromine. The bromine directs the ortho and the para. the ortho positions are both occupied. So the bromine is going to direct the para position. And then each of these acids, these are electron withdrawing groups. So they are going to direct the meta position. Of the ortho, they are going to direct the meta position. So this one's going to direct the meta, and this one is going to direct the meta as well. So this is going to come and direct the meta. So you can easily see that all of these groups, they are pointing towards the same carbon, which is this carbon over here. So you are going to end up getting just one product, which is the chlorination on this carbon. Keep the same groups. Nothing is happening to these groups in there. They all stay the same. So you have an acid here, and this is an acid as well. Now, if the groups oppose, then in this case, follow these rules. Always the strong activating group always wins over any other group, whether you're doing moderate, you're doing weak activating, or any deactivating group. By the way, I have posted the directing effect table on eCampus. This is the exam version, and you can use it for the exam. All the rules that I'm just mentioning, you can write them underneath the table without any examples. So you are not allowed to write any examples, okay? So let's have an example over here. Here, the groups will not reinforce each other. The NH2 is a strong activating group, and that is going to direct the ortho and the para position. This is an electron donating group. And this one is an electron withdrawing group, and it's going to direct the ortho and the para position. You can easily see over here that the groups are not reinforcing each other because the NH2 directs the ortho and it directs the para. Okay, and then the bromine, it's going to direct the NO2 to another positions there, not to the same positions. So the bromine is going to direct the NO2 to the ortho position, to it, and to the para position. So you can easily see that the groups are not reinforced in there. They are scattered. They are different. In this case, you need to prefer one group over the other. And this is the rule. You go with the strong activating group. Strong activating group always wins. So here, this is a stronger activating group. This is a withdrawing group. So strong activating group always wins over moderate activating, weak activating, and any deactivating. So if it wins, then the NO2 that is going to add is going to favor the positions of the NH2. So it's going to add ortho and para to just the NH2 in this case. So you're going to end up getting two products where the NO2 is going to add ortho and para. So this is going to be the NO2, and that is going to be the bromine over here, plus the NH2. You have the bromine, and then you have the NO2 added para to the NH2. So the NO2 will add ortho, and the NO2 will add para. Remember what we said last time about the static hindrance? So over here, you do have an accumulation of the groups on one side. So this is going to be a less favorable product, and this product does not form. So our major product in this case is going to be this product. Same thing in this example. These two, they don't reinforce each other. So I'm going to go with the stronger, and this is an electron donating group. It's a strong electron donating group. This is a weak electron donating group. So strong electron donating always wins, and if it wins, then the sulfonic acid that is going to add either ortho, or it's going to add para to the NH2, but the para position is already occupied, as you can see in there. So the para position is already occupied, so you only have one product, which is the ortho product. It can add either on this side or on the other side, and both are going to be the same because they're going to result in the same name of the chemical formed. So you're going to end up having your NH2 over here. The sulfonate or the sulfonic acid is going to add on this side or on the other side. It really doesn't matter. Both are going to be the same, and that is going to be only one product. Here I am forming my Cl positive. Again, you have electron donating a group, and this is a strong electron. It's a very strong electron donating group, and the NO2 over here is going to be a strong electron withdrawing group. So from our rule that strong activating groups, they always win over a moderate, weak, and any deactivating, whether you are working with a moderate or a strong deactivating group. So this one is a strong deactivating group, but the OH still wins in this case. Now, because the NO2 is present, we know that the OH is a very strong electron donating group. But the NO2 is going to decrease the reactivity a little bit of the OH. So you're not going to have a chlorination on both of the ortho and the para product at the same time. You are going to have chlorination on either the ortho or the para. So we are going to end up having the chlorine is going to add ortho to the OH, or the chlorine is going to add para to the OH. We have another ortho position, but that ortho position we are not going to consider because of aesthetic hindrance. So you're going to end up getting two products in this case. You're going to have your OH, and your chlorine is going to be ortho to it. Don't forget the nitro. Plus, you are going to have your chlorine para to the OH and the NO2. Again, the reason why not both the ortho and the para product got chlorinated at the same time, because of the presence of the strong electron withdrawing group that decreases the reactivity of the OH. If the NO2 was not present, then in this case, I would end up chlorinating both ortho and para product at the same time. Let's have another example over here. Normally, when you have three substituents on the benzene, go always with the strongest group. So the OH is a strong electron donating group. Bromine, this one is the strongest actually. This one is a weak electron withdrawing group. And this one is going to be a strong electron withdrawing group. The donating group is going to win over the withdrawing group. So whatever group I am adding here is going to be ortho and para to the OH. But the para position is already occupied, so I'm just going to have only the ortho position. So over here, the sulfonate is going to form the sulfonic acid ion, and my direction of the sulfonic acid will be ortho to the OH. So I'm going to end up getting just one product in this case. You're going to have your NO2, that is the OH, and then the sulfonic acid. This is going to be the SO3H in there and the bromine. Okay. This is another example over here. This is a strong electron donating group. These two are, both of these CH3s, these are weak electron donating groups. They are weak electron donating groups, so the OCH3 in this case is going to win. And if the OCH3 is going to win, then in this case, the OCH3 is going to direct the ortho position. Notice that the second ortho position is occupied, is a group number 1 in there. So the ortho position is on both of these carbons, and then the para position. The ortho position has a static hindrance, so this is going to be the para position. So I'm going to end up getting just the para product. So here you go. This is going to be my para product, which is the nitro, because I am adding here the nitronium ion. This is the NO2 positive. So I'm going to end up having the nitro. This is going to be my CH3, my CH3, and the OCH3 in there. The second rule is that if we have deactivating groups that are very strong, then in this case, those strong deactivating groups, they're going to win over the moderate deactivating groups, over weak activating groups, and over halogens. So they're going to win over everything in there that is not a strong activating or a moderate activating. So let's have an example. NO2 and the aldehyde. The NO2 is going to be a strong electron withdrawing group. So this is going to be the electron withdrawing group in here. And this one is going to be stronger than the aldehyde. The aldehyde is a moderate electron withdrawing group. Again, if you check both of these, they don't reinforce their products. They don't reinforce each other. So this is why you need to go with their strength in there. So the NO2 is going to direct the meta position, and this one is going to direct the meta position. But since this one is stronger, then you're going to go with the meta position of this NO2. You are forming your Br positive, so you are going to add the Br positive meta to the NO2. You can add it either to the side or to the other side, but avoid static hindrance. And if you add it to the side, then you're going to end up having a static hindrance. So this is why we are going to neglect the addition on the side. And our only product that is going to be formed is going to be the NO2, the aldehyde, and then your bromine is going to add meta to the NO2 on the side and not on this carbon, because you will have a static hindrance. The CF3 is a very strong electron withdrawing group. This is a strong one. And this one is a weak activating. So it is an electron donating group. This is the weak electron. And this is the only case where electron withdrawing groups, they win over electron donating groups. Whenever you have a weak electron donating group and a very strong electron withdrawing group, then the electron withdrawing group is going to win. Again, those two, they don't reinforce each other. This is why we go with their strength. What we are adding here is the chlorine ion. This is going to be the electrophile, and that electrophile is going to add meta to the CF3. So the meta position on this side is occupied. If this is carbon number 1, then this is going to be carbon number 3, and this is going to be carbon number 3. Those two are the meta positions relative to the CF3. This meta position is occupied, so this means that the chlorine is going to add only on this side, and you're going to end up having just one product. So that is the CF3. You have your chlorine and a CH3. Another example over here, if you have the nitro group and if you have a halogen. So we said that strong electron withdrawing group, these are deactivators. So this one is an electron withdrawing group, and it is a strong one. Those are going to win over halogens, over weak activating groups, and over moderate deactivating groups. So the NO2 now is going to win over the bromine. And if it's going to win over the bromine, then the sulfonic acid is going to come and add meta to the NO2. So it's going to come and add over here, and you are going to end up getting your product. This is the NO2. This is going to be the sulfonic acid. Notice that the attachment from the benzene to the sulfur, not to the oxygen and not to the hydrogen. And you have your bromine in here. The last case is for halogens and activating groups. So if you have a halogen in there and you have an activating group, we said that strong activating groups, they win over everything. Now for weak activating groups and halogens, always the weak activating group is going to win over the halogen. The strong deactivating group wins over the halogen, and the weak activating group wins over the halogen. So adding the nitronium ion from this reaction, then the nitronium ion, since this one is going to win over the halogen, then this one is going to direct the ortho and the para. So the nitronium ion are going to add ortho. Let's write it like this. So the nitronium ion is going to add either ortho to the CH3, or it's going to come and add para to the CH3. So you're going to end up getting two products in this case. That is the CH3, and this is the nitronium ion, or the nitro product now, since it's adding. And this is going to be the chlorine plus, here we are forming accumulation of groups on one side. So we're going to end up getting a less favorable product in this case. So you have your nitro group. In this case, this is going to be the major product. And this one over here is because of the static hindrance. This one is going to be not favorable to form. So if it is not favorable to form, just don't show it. You don't have to show this one. Just show the major product.